Hey guys, welcome to today's class. Have fun.
Today, today we'll be talking about waves and wave motion. So a wave is a disturbance which travels through a medium and transfers energy from one point to another without any permanent displacement of the medium itself. Now, what do you mean by this simple definition of waves? Now, waves are disturbances which travels through a medium, and by the virtue of passing through that medium, they transfer energy from one point to another without displacement of the particles of that medium. Now, we have a medium now. Now, now let's take for example, we have a partitioning now. Now, waves are disturbances which passes through a medium without displacing the particles of that medium. Now, this partitioning now, on the approach of, and let's probably say this is electromagnetic wave, which is a type of wave. And on passing through this medium, probably there are holes through diffraction or through various properties of wave, and coming out on the other side now. Now, it is noticed that the kinetic energy carried by this wave is being transmitted from point A to point B now without displacing the particles of this partitioning. So waves are disturbances which travels from a point to another without any permanent displacement of the medium itself. So in the traveling, in this distance covered by the wave, the kinetic energy is being transferred from a point to another point. So we have various types of waves. We have the mechanical waves and we have electromagnetic waves. Now I'm talking about mechanical waves. Now a mechanical wave requires a material medium for their propagation. Like I said earlier, waves are disturbances which pass through a medium. Now, the first type of waves we have, which are mechanical waves, are waves that require material medium. In the sense that they need a medium for their propagation. Now, for these waves to move from point A to B, they need a carrier. You can say a carrier or a material medium for its propagation. Now, example of these waves are water waves. Now, water waves now, example, the simple experiment carried out with the ripple tank experiment, in which you set up an apparatus and so in the ripple tank experiment, you have a setup in which you want to study the movement of water waves. Now, water has waves already. Now, in the flow of water, you have a particular pattern or direction in which the water particles move, they flow in the direction of the wave. Now, for mechanical waves, which an example is water waves, they require material mediums for their propagation. Now, for water waves to move now, water doesn't just move in, let's say, the atmosphere. No, it doesn't just move like compared to electromagnetic waves now. So these waves, they require a material medium for their propagation. So they require a particular medium for the propagation of their waves. So in this case now, this experiment was able to show us that water waves exist, and the material medium for the propagation here was the container in which the water was contained. So talking about mechanical waves, they require material medium for their propagation. The other type of wave we have electromagnetic, they do not require mediums. So in case of a mechanical wave that require a medium for its propagation, in electromagnetic waves, you just have the transfer of the kinetic energy from one point to another through space, that is through vacuum. So you don't have any means of transporting the wave, no means of propagation. So still looking at mechanical waves, we have various types of mechanical waves. Okay, example of mechanical waves are water waves and sound waves. So we have transverse waves. First example of mechanical waves is a transverse wave. Now, what is a transverse wave? A wave which travels perpendicularly in the direction of the propagation of the waves. Transverse waves, very simple wave. Now, this is the direction of propagation of the wave. And this is the vibrations of the wave. Vibrates up and down. Now, for transverse waves, they travel perpendicularly in the direction of the propagation of the waves. Now, transverse waves travel, as you can see the movements, to and fro, upwards and downwards, upwards and downwards. So in moving upwards and downwards, they are moving in a particular direction, which is a perpendicular direction. So because they are moving in upward and downward movements, but the direction of the movements is perpendicular to their means of propagation. Now this is the propagation means: up, down, up, down, up, down, up, down, up and down vibrations, but they move perpendicular to the means of propagation. An example of transverse waves is what we see in light waves. Light waves. Example is also what we see in X-rays, and you have radio waves also. Now, the movement or the direction of movement of the wave is perpendicular compared to its mode of propagation. So that's transverse waves. Now, we have longitudinal waves. Example, another type of mechanical wave is longitudinal waves. Now, for longitudinal waves, the vibration or propagation occurs in the same direction traveled by the waves. Now, in transverse waves, the direction of movement of the wave is perpendicular to the mode of propagation. But in case of longitudinal waves, now you have the mode of propagation of the waves is in the same direction compared to the direction of movement of the waves. So in this case now, you don't have to and fro, you don't have upward and downward vibrations. Now the vibrations are in the horizontal axis. So they vibrate this way and also follow the direction of the wave, moves in the direction of propagation. So this is just the basic difference between longitudinal and transverse. For transverse, the vibrations are perpendicular to the direction of the movements in water waves. Now, water waves, or you can see a simple rope. Now you have a rope now, and you swing the rope. Now they vibrate up and down, but still move on that axis perpendicular to it. But in longitudinal wave now, example is in sound waves now. Now sound waves vibrates in the horizontal direction, and the propagation of movements is also in the horizontal direction. So for longitudinal waves, you have sound waves, which we see when, and you can see it in vibration of musical instruments. You have probably a string, a vibration of this string now. The vibration occurs in the horizontal direction, not perpendicular to the direction of the movements of the wave. So also we have stationary waves. Now stationary, when you say stationary, you mean something that is standing or something that is static and isn't moving. Okay. Now when two simple harmonic waves of the same amplitude, frequency and time are traveling in opposite directions in a straight line, we have a stationary wave. Now a stationary wave is simply due to the interference of two waves in opposite directions. Now you have a first wave and you have another wave now. And this was the first wave. wave 1, and this was wave 2. Now, a stationary wave is formed due to the interference of two simple waves moving in opposite directions, but they have the same amplitude, they have the same frequency, and the same time of propagation. Now, as we move further, we'll be defining some of these terms: amplitude, frequency, the period, and so on. So, but for a stationary wave now, it's simply due to the interference of two waves. They have the same amplitude, they have the same frequency, and the same time of their propagation, but they move in opposite direction. So for one which is moving in, say, the positive direction, two is moving in the negative direction. So these are stationary waves. An example of a stationary wave is sinusoidal. A sinusoidal wave, something that we've seen here. An example is this now. So another example of a mechanical wave is a progressive wave. A progressive wave. A progressive wave, now, a traveling wave moving continuously from one point to another with the same frequency, same amplitude, but different phases is a progressive wave. A progressive wave is a traveling wave. It is always in continuous motion. Fine. Traveling wave moving continuously from one point to another, same frequency, same amplitude, but different phases. So by progressive wave now, you have a wave, like this. This was the first wave which moved this way, and this was the second wave. This was wave 1, this is wave 2. Now the waves have the same frequency, the same amplitude, but different phases. Now, talking about phases now, we are talking about a phase is the displacement of the vibrating particle at any instant compared to the amplitude. Okay, I'll be explaining those terms, but simply quickly to explain a progressive wave. Now, a progressive wave is a wave starting from a point and continuously moving from one point to another. Same frequency and amplitude, different phases. Now, for this wave, you can have a particle here, another particle here. You have a particle of the wave here, particle of the wave, another particle here. Now, these two waves are progressive waves. They are continuously moving, but the particles can be at different phases. Now, for this first wave, this particle here compared to a particle here now, a phase, this is one phase, this is another phase. They are progressive waves continuously traveling, but their particles are at different phases, different amplitudes compared to the amplitude of the vibrating particle. So that's what we mean by a progressive wave. Now, a longitudinal wave can be a progressive wave. A longitudinal wave can be a progressive wave because in a longitudinal wave, you have a continuous movement. The vibration is along the mode of the propagation. Okay, so also the second type of class of wave we have is electromagnetic waves. Electromagnetic wave. Now, electromagnetic waves, these are waves that do not require a material medium for its propagation, but move successfully in free space. They travel with the speed of light, associated with light, and are undeflected in electric and magnetic fields. Now, on introducing waves to us, I made mention of disturbances that travel through a medium, transfers energy from one point to another without displacing the material medium. For mechanical waves, I said they require material mediums or a carrier. But in case of electromagnetic waves now, electromagnetic wave, they need no carrier. No carrier is needed for electromagnetic wave. They move in free space. Now, free space is vacuum, air, and the speed of Now, the speed of light in a vacuum is 3 times 10 raised by 8 meter per second. So for electromagnetic waves, they don't require a material medium. They do not require a material medium for their propagation. They move successfully in free space and they travel with the speed of light. Now, because they move in air, vacuum, they travel with the speed of light. They are associated with light and they are undeflected in electric and magnetic fields. Now, because mechanical waves, they need material medium for their propagation. So on encountering electric field or magnetic fields, they are deflected. But for waves which travel in vacuum, which are electromagnetic waves, they move with the speed of light. So they are not deflected in electric fields and magnetic fields. Typically, we also have different types of electromagnetic waves. So, and types of electromagnetic waves will be seen in the electromagnetic spectrum. Now, the range of all radiation possessing the special characteristics of electromagnetic waves and arranged in order of their wavelengths or frequency. Now, we have different types of mechanical waves, which I explained: the transverse, the longitudinal, progressive, etc. Now, for electromagnetic waves, now they are grouped into a class known as the electromagnetic spectrum. So these are all the radiations, forms of radiation, because electromagnetic waves move in vacuum, they move in space with very high speeds. So in that case, they emit particles, they radiate particles, energy moving from one point to another. But the range of all these radiations possessing these characteristics of electromagnetic waves arranged in order of their wavelength or frequency. So you have 6 types of electromagnetic waves in the electromagnetic spectrum. Revox G. So we have Revox G. It's short form for us to remember them. So now we have R, which stands for radio rays. I stands for infrared rays. V stands for visible light or lights that we can see. U stands for ultraviolet rays. X stands for X-rays, while G stands for gamma rays. So we have 6 radiations or 6 waves in the electromagnetic spectrum. Now they are arranged in the order of their wavelength and frequency. Now from left to right, you have the increasing velocity and frequency. So as you move from top to bottom now, the velocity increases. So the velocity of gamma rays are much more faster than radio waves. The velocity of X-rays are much more faster than infrared rays. So as you move downwards, you have increase in velocity, you have increase in their frequency. And the frequency talks about the number of cycles a wave travels in 1 second. Now, because gamma rays are very fast, they can cover more cycles per second when compared to radio waves. So there is an increase in their frequency, but decreasing wavelengths. So in this case now, you have, as you move downwards, the wavelength, which is represented as gamma, decreases. So this can be explained simple now. Now this is radio waves and this is gamma rays. Now radio waves have a lower velocity when compared to gamma has a larger velocity. Now because gamma has a large velocity, it covers more cycles per second, frequency F. Now because radio waves have a lower velocity compared to gamma, their frequency, the number of cycles it's travel in 1 second, is smaller. Now if gamma rays have large velocities and large frequencies, then the wavelength will be smaller because gamma will travel very fast, very fast, very fast, very, very fast. And the wavelength is the distance between 2 crests, which I'm still going to explain those terminology. But since radio waves have lower velocity lower frequencies, their wavelengths are larger compared to this. But this is faster, higher frequencies, but lesser wavelengths. So moving downwards now, you have increase in velocity, increase in frequency, but decrease in the wavelengths. All right, so we have some properties of waves which we are meant to understand. So we have 5 basic properties of waves. Number 1, we have reflection. Now, by reflection, we mean the change in direction of waves when they hit an obstacle. And you have, let's take for example, sound waves now. Now, sound meets an obstruction. It meets this obstruction. Now, the property of that wave to hit this obstruction and bounce back is known as reflection. So by reflection, you mean the change in direction of waves when they hit an obstacle. This is referred to as reflection. Now, reflection depends on the type of obstacle they meet. Now, if it meets a straight obstacle, of course, you expect a very plain or parallel wave. Now, if it meets a rough obstacle, of course, the reflected wave will also be affected. So, reflection is the change in direction of waves when they hit an obstacle. All right, so the next one we have refraction. By refraction now, I'm talking about refraction talks about the change in wave direction and when it enters a different medium of propagation. Now, for reflection, you talk about change in direction when it hits an obstacle. Fine. But for refraction, recall that wave travels through a medium, with or without a medium. Fine. Now, for waves traveling through a medium now, it is not hitting an obstacle, but there is a change in its direction when it enters a different medium. Now, what this means now, you have water now. This is water, a wave traveling in water now. Now, on reaching a particular point, the level of water decreases. And this water was at maybe 10 meters, but the water level here is now at 3 meters. So, the mode of propagation of the wave in water of height of 10 meters will be different compared to this. In this case now, you have a larger wavelength. Compared to here, you have a more tinier wavelength due to the shallow depth of water. So refraction is brought about by the change in direction of waves due to the change in the medium of propagation. So in this case now, we talk about refractive index now. We talk about the velocity in one medium, velocity in another medium. So moving in deep water now, you have a velocity v1. Moving in shallow water, you have a velocity v2. So refraction talks about the wave direction, change in wave direction when it enters a different medium of propagation. So now we also have diffraction. Now by diffraction, it's a phenomenon in which waves bend round obstacles, or the spreading of waves after they pass through openings or holes. And what does this mean? You have waves moving. Now, on meeting an opening, now this is an opening. Now the waves were coming, traveling through the medium or without a medium. Now on meeting an obstruction now, but this is not an obstruction in the sense that it is not a full obstruction. We have an hole, a space here now. So the ability of waves to bend around obstacles is what we refer to as diffraction. So in this case now, the wave particles begin to reduce So, okay, proper drawing here now. You have a wave moving. I'm approaching a hole now. The wave tries to bend in order to attain this and pass through the hole. So the ability of waves to bend round obstacles is what we refer to as diffraction. So it moves with shorter wavelengths and begin to spread back. It spreads back and begin to move with the same wavelengths in which it was moving it. So what happens is that the smaller the hole, the smaller the wavelength, and the greater will be the spreading. And you have a small hole now. And because there's a small hole now, there will be a smaller wavelength and the greater the spreading of this wave. But in case now you have a larger hole and the wavelength, the greater the hole now, the wavelength will be bigger and the smaller will be the spreading. So for a large hole now, it just passes through. And the spreading is not that noticeable. So diffraction is the ability of waves to pass through holes or pass through obstacles. Okay, so up next we have interference. Now interference simply means the crossing of two waves crossing each other's paths by the word interference. Now when we say interference, we simply mean crossing each other's paths, interfere into one's other affairs. Now for interference of wave, it occurs when two waves from a source they cross each other's paths. So you have a wave from a source now, and you have another wave from that same source, and they are crossing each other's paths. So the interaction of two waves moving simultaneously through the same medium is also referred to as interference. So interference is the interaction of two waves which move simultaneously through the same medium. Now you have two types of interference. Now you can have constructive interference Now, what do we mean by constructive interference? For constructive interference now, in constructive interference, as the throw or crest, now this is the crest of the wave and this is the throw. Now, as the crest of one wave arrives, the crest of the next wave arrives. As you can see here now, you move here, as the throw arrives, the throw of the next wave also arrives. Now, as the crest here arrives, the crest here arrives. Here arrives. So in constructive waves now, the crest of one wave arrives simultaneously as the crest of the second wave to form a constructive wave. Or you can simply say the intersection of the nodes of wave, the same phase of waves in the same phase. Now this wave moves with a crest, it comes here, goes downward, the trough goes down. Now this wave also moves with its own crest, comes here before it goes downward. So this node is the interaction of the crest and the trough. So the points in which this node now, you have the interaction of crest to meet trough, trough to meet crest, crest to meet trough. That is a constructive wave. Now another instance, you have this is one wave and this is another wave. And this is a destructive wave because the crests, they do not arrive simultaneously. Now as this first wave moves, this is its crest. This next wave crest is supposed to move also, but instead it moves in opposite direction. Trough. So the movement of the crests of one wave not simultaneous to the movement of the crest of the next wave is what forms destructive wave. So if the crest of one wave does not arrive simultaneously as the crest of the other wave arrives, then we have a destructive wave. So in destructive waves now, the nodes now, they have zero energy, because in this case now, you have crest and crest. Two crests come to meet at this point, maximum energy. But in this case now, you have a crest and you have trough. That means you have plus and minus coming to meet here. You have zero. So the maximum energy there is zero. In this case now, you have one crest positive and another crest positive. You have maximum energy here. So in constructive interference, you have maximum energy at the nodes, whereas for destructive interference, you have zero energy at the nodes of their interference. So last property of wave we're looking at is polarization. So talking about polarization now, polarization simply talks about the confinement of waves in one direction. Confinement of waves in one direction. If you recall now, we say longitudinal waves, their mode of direction is perpendicular to the vibrations, whereas for transverse waves, the mode of vibration is in the same direction. So if longitudinal waves move in that direction, now to make transverse waves move also in the direction of their waves is what brings about polarization. Now polarization is the construction of fluctuations of vibrations to vibrate in one plane. So you have a transverse wave now. You want this transverse wave to transmit its energy in just one plane of direction like longitudinal waves. So polarization simply means the confinement of waves in one direction, which occurs definitely only in transverse wave, because it's only a transverse wave you can convert to move in one plane of direction, because a longitudinal wave already moves in that direction. So an example is what you see in light waves. So it's referred to as plane polarization of light. Now the plane polarization of light means the fluctuations or the vibrations are being made to vibrate in one direction. So for light waves now, which move transversely, the act of phenomenon in which these vibrations are being converted to move in straight lines is what referred to as polarization. So we say polarization of light waves. So quickly we'll be looking at some terminologies now in wave motion. And before we start solving examples, there are lots of questions on waves. Waves are very common. The questions are very common in WAEC, so we have to be fast. Okay. So I have amplitude. Now the first terminology we're looking at is the amplitude. I'll be talking about amplitude when I talk about waves, types of mechanical waves. The amplitude is the maximum displacement from points of rest. This is the point of rest of the wave. Now the maximum displacement is what's referred to as the amplitude. So the maximum displacement of a wave from point of rest is what we refer to as the amplitude, which is in meters. So the displacement of this wave to a maximum point back to the point of rest displaces again to the point of rest. Maximum displacement back to the point of rest is what we refer to as amplitude. So we have phase. Now, talking about phase now, the ratio of displacement of the vibrating particle at any instant to the amplitude of the vibrating particles is what we refer to as phase. So when we say particles in a wave are in phase, now what do we mean? You have a particle here moving in this direction, and you have another particle here moving in this direction. Now you can see the ratio of their displacement to the vibrating particles at any instant. Now the ratio of the displacement of this particle, the distance here, and also the distance here. Now these two have the same distance, same maximum displacement from the origin, also for this particle. So these two particles are said to be in phase with one another. because the ratio of their displacement at any instant to the amplitude of the vibrating particles is the same. So this particle A and particle B are said to be in phase. So also we have vibration. Now the to and fro movement of a particle from one position to the other and back is what we refer to as vibration. Vibration, simple, to and fro movement. When we say something vibrates, so the movement of a wave from here up, down, and back to this point is what we refer to as a vibration. So vibration is just the up and downwards movement from a particular position back to that position is what we refer to as vibration. So if this particle moves from point A to B, it's moved from A upwards and downwards to B. So that is vibration. So also we have wavelength. Now the wavelength is the distance between two successive crests or trough of the wave, and is expressed as lambda. Now I've been using these terms in the initial part of the class. I said I've explained terminology. Now the distance between two successive crests or troughs of the wave is what we refer to as wavelength. Okay, this is the wave. Like I said earlier, this point. Now the maximum point here, the distance from here to here is the amplitude. But this point of the wave is what we refer to as the crest. This point is what we refer to as the trough. So this point also is a crest, and so on and so forth. The distance between a crest and another crest gives us the wavelength in meters also. So the distance between one crest and another crest is the trough, or the distance between a trough and another trough is also wavelength. So just the distance between two successive crests is the wavelength. So now we have period. And period is the time taken for one complete oscillation. T, it is represented as capital letter T, and it is in seconds. And the time taken for one complete oscillation is what you refer to as the period. And what is an oscillation? We say vibration now is the movement to and fro. Now, one complete vibration is what we refer to as an oscillation, or two vibrations. Now, the vibration is to and fro. This is to, now this is fro. Now, this is one oscillation because you have one and one. So, this is one oscillation. The oscillation is a complete cycle from here to here and back to the starting point. So this is one oscillation. So the time taken to complete one oscillation, the time taken is referred to as the period, capital letter T. The period, the time taken for one complete oscillation. Now we have frequency. Now frequency talks about the number of cycles which the wave completes in 1 second. Frequency is the number of cycles per second. It is represented in Hertz, Hertz. This is the unit for frequency. In summary of all the terminologies now we should be using to solve questions now. Amplitude, the first one was the amplitude. The amplitude is the maximum displacement from the point of rest. The point of rest to this point is the amplitude. You can see here, from here to here, distance from the point of rest now to its maximum displacement is the amplitude. Now the phase is the ratio of displacement of any particle to the amplitude. Now for various particles, you have different particles at each point of the wave. Now for any particle which have the same displacement compared to the maximum displacement, they are in phase with one another. So a particle here and let's say a particle here which are the same displacement are in phase with one another. Now for vibrations, we talked about the to and fro movements of the particle, that's vibration. Now for wavelength, we said the distance between one crest to another crest is the wavelength. Now for period, we said the time taken to complete one oscillation. And oscillation is 2 vibrations. Vibration 1, vibration 2. So this is an oscillation. From here to here is an oscillation. The time taken to complete one oscillation is the period T. Now frequency is the number of cycles per second. And the number of oscillations you complete in 1 second is the frequency. So period is time taken to complete one cycle. Frequency is the number of cycles you take in 1 second. So we should not intertwine them together. So finally, we'll be looking at the wave representation. And these are formulas we'll be using in solving waves. We have period, and the period is equal to 2 pi over W. W here is the angular velocity. You have another formula, V equals to F lambda. And these are formulas we're going to be using when solving. So I want us to master them. The period is equal to 2 pi over W. And this is velocity, frequency, wavelength. V is equal to F lambda. And also have the angular velocity is equal to 2 pi F. So also you have the period is equal to inverse of the frequency. Period is inverse of the frequency because your period says number of cycle in number of the time taken to complete a cycle, the time taken. Why period and why frequency talks about cycles in 1 second. So for period, you have for period you have time taken to complete 1 cycle. For frequency, you have the number of cycles, the number now completed in 1 second. So you can see they are intertwined. So it gives us the period is the inverse of the frequency and the frequency is the inverse of the period. So finally, we have an expression now for the wave representation. You have y equals to a sine wt minus phi. So a here gives us the amplitude. This is the angular velocity, time, and phi. Now further simplification, we have these two formulas. I'll be making use of these formulas. So these are the most important formulas to be using to solve in wave motion now. So A here is the amplitude, which I explained. Pi, which is 3.142. This is lambda, which is the wavelength. V is the velocity. T is the time. X is the horizontal displacement. And the representation, you have y-axis and you have x-axis. Movement in y-axis, movement in x-axis. So these are the formulas which we'll be using. So now we'll be solving past questions on waves and be seeing how to apply these formulas. So first question we'll be solving here. This is a NECO past question 2019. And this is one of the objective questions. It says a wave represented below moves with a velocity of 0.5 meter per second. Now we are asked to determine the period T. Now to study this diagram, and you can see from here now that this is the y-axis, x-axis, and these distances are the wavelengths. Now to find the wavelengths now, recall that the wavelength is the distance between two crests or two troughs. Using crests now, so each distance here is 0.5, another 0.5, another 0.5, 0.5, 0.5. So from here to here is 0.5, here to here is 1, here to here 1.5, here to here 2, here to here 2.5. So to find our distance now between the two crests, so from here to here is 0.5, 0.5, 0.5, 0.5. So our wavelength is 2 meters. So our wavelength is 2.0 meter. Because distance from here to here, that's 1, 2, 3, 4. 4 times 0.5 is 2 meters. So we have to find the period T. Now, if you recall that V is equals to F lambda, and recall that T is equals to 1 over the frequency. So we have velocity given, we don't have the frequency, but we have our wavelength from the diagram. So to find our frequency is equals to V over lambda. So V is 0.5, lambda is 2, it gives us 0.25 Hertz. And to find our period T, now T is equals to 1 over frequency. So 1 over 0.25 gives us 4 seconds. So the answer here is D. So we have another example here. It says a plane wave passing through a narrow slit spreads out. This phenomenon is known as what? Of course, it is diffraction. I said diffraction is the phenomenon in which waves try to bend around obstacles. So you have obstacle, you have a wave coming in. The ability to bend around it and continue its motion is known as diffraction. Interference is movement of two waves. Polarization, vibration in a straight line. Reflection, change in direction of a wave when it hits obstacle. Refraction, change in the direction, change in propagation when it moves from one medium to another. So a plane wave passing through a narrow slit spreads out due to diffraction. So still on the same past question. 26 now. It says the position of visible light in the electromagnetic spectrum is between what? So you have the electromagnetic spectrum, which I explained earlier, is Revox G. Radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So you are asked, what is the position of visible light in the spectrum? V is visible light. So visible light is in between infrared rays and ultraviolet rays. So ultraviolet rays and infrared rays. So the answer here is D. So we have another question. Okay. It says the wavelength of sound produced by vibrating tone is 1.5 meters. The wavelength of sound produced by vibrating tuning fork is 1.5 meters. Calculate the frequency of the vibration. The speed of sound in air is 330 meters per second. So recall that V is equals to F lambda. They ask to find frequency. So frequency will be equals to V over lambda. So our frequency is, velocity is the speed of sound, the wavelength, which is 1.5. So this gives us 2.2 times 10 raised to 2. Our answer here is option B. So another past question here. This is the theory part. I'll be picking the questions that pertain to wave now. You have question 6 here. It says explain how the two types of wave interference are formed. So I'd like us to recap from the class. The two types of wave interference are constructive and destructive. Constructive wave is formed when two crests of two waves arrive simultaneously, while destructive interference is formed when, as one crest arrive, the trough of the other wave arrive simultaneously. So in constructive wave, the nodes have maximum energy, whereas in destructive waves, the nodes have zero energy. Now that question here in this same exam paper, question 14, this is what is a wave? State two differences between light waves and sound waves. Now what is a wave? A wave is a disturbance which travels through a material medium, transfers energy from one point to another without displacing the properties of that material medium. It says two differences between light waves and sound waves. Now, what is light wave? What is sound wave? Light wave is an electromagnetic wave. Sound wave is a mechanical wave. So what is the difference between a mechanical wave and an electromagnetic wave? Now, for light wave, which is electromagnetic, it requires, number one difference now, It requires a material medium for propagation, and number two, it moves with the speed of light. Now for sound wave, which is a mechanical wave, light wave is an electromagnetic wave. It does not require a material medium, and it moves with the speed of light. For sound wave, which is a mechanical wave, it requires a material medium and it does not move with the speed of light. So I have another past question. This is a WAEC past question now. 2019 also. The other editor was a NECO past question. I say, which of the following waves is not mechanical? Waves in pipes, water waves, radio waves, sound waves. Now, sound wave is a mechanical wave. Radio waves is an electromagnetic wave. Water waves, mechanical wave. Waves in pipes, water waves also is mechanical. So radio waves, because of, if you recall from the electromagnetic spectrum, you have revox G, and you have radio waves there. So it is radio waves that is not a mechanical wave. So still on the same past question. Now, question 19 here says a transverse pulse of frequency 9 Hz now travels 4.5 meter in 0.6 seconds. Travels 4.5 meter. The distance traveled and the time 0.6 seconds. Calculate the wavelength of the pulse. You know the wavelength. Now it says a transverse wave. Recall a transverse wave. It's a transverse wave. Direction of propagation is perpendicular to movements, the propagation of the wave. Vibration is perpendicular to the direction or propagation of the wave. It says it has a frequency of 9 Hz, travels 4.5 meter in 0.6 seconds. Calculate the wavelength. Now you recall that V is equals to F lambda. We have the frequency. We're asked to calculate the wavelength, but we don't have the velocity. And recall that velocity is what? Distance over time. Now, since velocity is distance over time, we have the distance, which is 4.5, and we have the time covered, time taken to cover that distance. Now equals to 9 times the wavelength. So 4.5 divided by 0.6, and this. So our wavelength will give us 4.5 divided by 0.6, or into 9. Sorry, divided by 9. Change of subject of formula. So this gives us 0.83 meters. 0.83 meters is our answer. I have another question here, question 33. It says, which property of a wave remains constant when the wave travels from one medium into another? You have a wave traveling from one medium to another. This has its own refractive index. This has its own refractive index. So a wave traveling from one medium to another, that's refraction now. The amplitude would change. The wavelengths would also change. Now, what about the velocity and the frequency? The velocity will remain constant velocity, whereas the frequency will change. Now recall that the frequency is the number of cycles obtained in a second. Now, for this wave, upwards and downward, the time taken to complete this cycle will be different from the time taken for this wave to complete its own cycle. So moving from one medium to another, the frequency will decrease or increase because the medium has its own refractive index, but the velocity, the speed of propagation of the wave will remain constant throughout, because either is moving with the speed of light or not. So it's the velocity. So you have another question, question 40. I said in the diagram above, the time taken to trace a wave between P and Q is what? How many periods? Recall that a period is the time taken to complete one cycle. That is our period. The time taken to complete one cycle is a period. So the time taken to trace a wave between P and Q is how many periods now? Between P and Q, how many periods do we have? Now, a cycle is distance between two crests. And this is one crest. This is another crest. Q is at this crest. So the distance from here to here, that is one crest. That is one period. That is one period. The distance from here to here, the time taken to complete another cycle is another period. But in this case now, we don't have P at this point. We have P at halfway through it. So this is 1.5. So this gives us 1.5 periods. So the time taken to trace wave between P and Q is 1.5 period. Because this is one throw to another throw, one period, one throw to another throw, 2 periods, but we are stopping at this point, half. So it is 1.5. Another example here says, which of the following properties is not exhibited by sound waves? Sound wave is a mechanical wave, and sound wave is a longitudinal wave. So sound wave cannot be polarized. It can be diffracted, it can be interfered, and it can reflect. But sound wave cannot be polarized. Light wave, which is an electromagnetic wave, is the one which can be polarized. Okay, the last example we're looking at here from the reference material Essential Physics says a wave is represented by the equation y equals to 2 sine pi into brackets 0.5x minus 200t. And this is the representation of the wave. So where all distances are in centimeter and time in second. For this wave, calculate its frequency, its wavelength, and its speed, that is v. It's an echo pass question. So we're asked to find the frequency, wavelength, and the speed from the equation of the wave. Now to solve this, now you have F lambda and V, and recall that you have a formula V equals to F lambda. And this formula is very useless in this setting. In the sense that we don't have the velocity, we don't have the wavelength, and we don't have the frequency. So in this case now, let's be using the formula for wave representation, which I showed you at the explaining the last part of the class. So I'm using this formula now. So all what you simply need to do is just to compare coefficients. Now comparing these two equations together, this is the standard form which we are given. So you write this standard form. We have a sine pi 2ft minus 2x over lambda. This is the standard form. I just rewrote the standard form so that I can be able to compare with the question given. Now in comparison with this, y equals to y, a equals to 2, a equals to 2 centimeter. So our amplitude is 2 centimeter. Now I have sine pi, I have sine pi. Now here I have 2ft, here I have 200t. So 200t equals to 2ft. I have time, I have time. So I have 200 equals to 2f. So f gives me 100. So I'll be able to find the frequency, which is 100 Hz. Now the last thing I have here is 0.5x, and I have 2x over lambda. So 0.5x equals to 2f over lambda. 0.2x comparison 0.5x 2x over lambda. For this I compare 200t to 2ft. So this same way, so I can cancel both the x out. So I have 0.5 equals to 2 over lambda. So lambda will give me 2 divided by 0.5. So lambda will give me 4 centimeter. So using the wave representation now, I was able to interpret the equation of this wave to be able to bring out my velocity, my frequency, and lambda. So now I can find my velocity from v equals to f lambda, and that gives me 100 times 4. So my velocity is 400 centimeter per second. Thanks for listening.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.